are going to start the lecture on nanotechnology in chemical engineering. So, today we will discuss about the various method of synthesis. So, we are discussing about the physical method of synthesis. So, today basically we will discuss about chemical vapor depositions. So, in chemical vapor depositions, basically these are the components or the content components we will discuss. There are variants that we will discuss. What are the various type of CVD process are used or available, then basics about the CVD, then growth mechanism of CVD, CNT growth by CVD, single layer or multi-layer graphenes, 2D materials growth by CVD. These are the components will be discussed. Okay. So, as we said that CVD, that is the physical vapor chemical vapor depositions method. So, in this method we can prepare thin films for a particular materials that is in nano range that we can prepare. So, for that we have to use some gaseous reactants that would be heated up at a high temperatures and then in presence of catalyst. So, may be deposited on a substrate. So, this is the basics, means similar like we have discussed the physical vapor depositions, that is evaporation and sputtering technology, similar like that. So, this is also. So, here first heated a substrates at a desired temperature that may be 700, 800, 1000 degrees centigrades, and then in that substrates when it is high temperature, a source gas, that is the source of that may be carbons or any metal oxides, that would be, or maybe any inorganic organic materials, that would be take part in the reactions. Some chemical reactions will be taking place over the substrates in presence of catalyst or in absence of catalyst, and then that would forms a layer that is very thin layer. So, that is we can say if thin films that would be produced over the surface of the substrates. Okay. And then that thin films we can recovered or we can collect or we can reuse for any particular applications. So, here in this particular CVD methods there are some advantage and some disadvantages too. So, in this process we can enable or enable depositions that rate that would be deposited that particular films or a particular carbons or that particular materials. So, we can control the quality of that materials, also we can get high quality of that products that can be distributed or formations when it is synthesized by using CVD methods. Also there is some disadvantage too when these reactions will going on, means in the CVD process. So, that gaseous molecules or inorganic or organic materials that would be the precursors for this process. So, when it would be react with that substrate or catalyst or in presence of that gases, so then some byproduct formations is there, some highly toxic compound formations is there. So, these are the things, these disadvantage in this particular process. Otherwise, that process is very good to prepare a thin films formations. Okay. So, this CVD process widely used in industry due to its simple instrumentations, easy processing and possibility of depositing different type of materials, and it is economically viable. So, therefore, industrially it is widely used. The CVD, there are some various type of CVD, means the CVD process means basic is any starting material precursor that may be organic, inorganic, that would be source of that desired film formations. So, whence that films would be formations, there is some reactions I said. So, that reactions would be take place by different type of CVD. We can consider depositions patterns is different. So, it depending upon the source gas precursors. So, we can having low or high pressures that we can use when the CVD process will take place. So, either we can use 1 atmospheric pressures or maybe vacuum conditions we can conduct the CVD process. So, depending upon the source gas pressures also we can classify into low and high pressures. Also geometrical layout of the reactions chambers, the reactors we have to use for this particular CVD process, it we can maybe horizontally or maybe it is vertically or maybe some inclined angle. So, it may be, so depending upon that, so we can use or we can classify a different type of CVD method or variants. So, then temperature. So, temperatures is one of the parameter for the CVD process. So, here hot or cold wall, plasma, photo lasers, that also can be used when CVD process, means using a horizontal chemical or vertical CVD, low pressures, atmospheric pressures, hot wall, cold wall CVD, plasma enhanced CVD, and photo assisted CVD or laser CVD. So that way we can classify or we can categorize the CVD process. So in particularly I said the horizontal chemical vapor depositions or vertical CVD. So in these two process, the substrate will that would have to placed in that particular reactor, so that would be mounted in horizontally or maybe it is vertically, or we can say it is tilt some angles to adjust the gas flow. Okay, so through that means, so when in the CVD process I said hot chambers, that is called reactors, that may be ceramic or quartz or maybe some other materials that can be used. So through that the reactant or substrate would be reactants materials or reactant gases that would be passes through this. So it may be horizontally, vertically, or maybe some tilt angle will be placed. Okay. So and in low pressure CVD or atmospheric pressure CVD, I also said that the working pressures is different depending upon that. So we can say it is low pressure or atmospheric pressure CVD. In low pressure usually vacuum pump is used for this process. So vacuum pumps, what that would do, that is actually drives the gas that would be creates the vacuums, and through that vacuum, so that gas would be injected or pulse injected inside of the reactor. So that would be a pass through this surface of the catalyst, or reactions will be take place, and that way depositions or films formations would be there. And in atmospheric pressures, that is atmospheric pressure or normal pressures, we can operate that system. So here does not require that pump to flow the gases for this process. Okay, reactive gases or the reactants that we need to pass through this process. And then hot wall and cold wall CVD also I said. So in hot walls, the entire reaction chamber is heated by a electrical furnace. So electrical coils that would be surrounded in the entire surface or external surface of that CVD reactors. And in case of the cold walls, the only the particular positions where the substrate will be placed, that particular points or locations will be heated up, and rest of the surface or reactors walls that remains cold or normal temperature. So in this process we can do, or advantage is that rapid heating and cooling process we can maintain through this process. And other variants that is of CVD is plasma enhanced, photo assisted, laser assisted, that also are possible. So for the CVD process, in plasma actually a partially ionized high energy gas that would be generated in plasma enhanced process, that heat or heated up, that would be by using DC currents or radio frequency voltage or microwaves, that could be the source of heatings that can be means inserted or coupled with that reactors. So as a result, so we can get a measured drop of the reaction temperatures during that process. Okay, so in photo assisted or laser assisted process also, there's we can use a light from a high intensity lamps, so, or laser that can be used to promote the depositions, means when that CVD process will take place. So then any lasers that would be, instead of any coils or a furnace, so only some source of high intensity lights or maybe laser can be used for this process. Okay. So depending upon various sources of the gas pressures, geometry and temperature, so you have classified the different variety of CVD. So apart from that, so we can also categorize the CVD process by metal organic CVD, that is also here some volatile toxic liquids that may be used as a precursors for this process, that usually to synthesis group 3 and group 5 compound for semiconductors, and that is applied for optoelectronics. So in that case metal organic CVD, that process can be used. Then so hot filaments or wire CVD, that also can be used. In that case a heated filaments that made of tungsten or molybdenum wire or tantalums, that wires that can be used, and that would be suspended instead of heating. So it would be suspended above the substrate. So in a particular locations we can place the substrate, and above that that filament would be suspended, and where that filaments would be placed, and over that filaments thermal depositions would be there, and that precursor should be adsorbed over that particular filament surface, and then in the cold surface that film formation should be there. So this type of inorganic film formations such as amorphous silicons or silicons nitrates that can be deposited over the surface by using hot filaments or wire CVD, that can be possible. So, okay, so in other type of CVD, that is initiated CVD, that is it is similar to the hot filaments or wire CVD, similar to the here's growing up electrically insulating polymer thin films formations that is possible by using this, and initiator and monomers vapors, that would be initiator and monomer vapors, that is vapor phase, that would be used as a reactants, that would be absorbed and then undergo chain growth polymerations on the cool substrates. So by that way we can prepare say thin films for a particular organics that material. So in this process actually what are the functions group presence that can be preserved. So suppose any organic materials polymers we have taken monomers. So if that monomers consisting of a specific type of functional groups that we can preserve, since here's the surface cool substrates over there, the films are polymerization chain growth, so that would be deposited over there, that can be forms. Okay. And then oxidative CVD, this is also another kind of CVD. So in this case oxidants and monomer vapors that would be utilized for this particular CVD process, and which undergo some spontaneous reactions upon adsorptions over the surface of the substrates, and then step growth polymerization process would be there, and then as a result we can get some film formations. That film may be conducting semi-conducting polymery films that would be deposited in this particular substrates. Okay. And then atomic layer depositions or molecular layer depositions, that is also another kind of CVD variant. So here these two type of CVD variants, here layer by layer film formations that we can develop for a particular substrates. So here between layers also different precursors that may be present there, that may be parched out by the carrier gas also. In this process we can advantage to formations layer by layer depositions of a particular films. Okay. So the basic process in this I said that CVD process. So here's one particular reactants that we have to use, that is the source for that particular nanomaterials or nanofilm formations, that would be passed through a substrates or catalyst over there. See, here you can see in this CVD process, this is substrates we have taken here, whence they will come at a particular temperature over the surface. So that may be over the surface, and maybe some reactions will be take place over the surface, and then with film formations or film formations or nanoparticle formations, some intermediate or gaseous byproduct formations would be there. That would be, this is byproducts, and this is also any intermediate also product may be formations there, and this is film formations actually. So whence that gas molecules will be decomposed, and that elemental carbons or maybe graphenes or CNT type of material that would form or deposit in the nanofilm formations would be there in over the substrates. So in this particular process I said, so temperature is also very important. So with the various parameters, reactant components, means gases, that is the starting materials that would be used for this particular process. With that reactions also is important. So the reactions temperature for this furnace, that usually 300 to 1200 temperature that can be maintained for this particular CVD process. Here if you look into hot wall and cold wall process, so here you can see, so is this first one, that is the hot wall. So here's some gases or vapor that would be passed through the furnace. So here's this is the hot elements, and this is the substrate is placed here, and outsides of this substrate, that is heating elements or the filaments would be placed. So outside of that furnace tubes that would be heated by the heaters. Okay. So and in cold wall CVD, here substrate is here, so here only particular locations that filament is present. As a result it is not heated up throughout the walls. Okay. So in as a result rest of the space that remained cold surface in this particular process. So in this particular hot wall the deposition of reactors wall each possibility is there. Whatever the gas phase reactants that would be deposited over the surface of the hot walls, and in case of the cold walls, so that type of depositions of that nanomaterials or nanofilms that we can avoid by using cold wall CVD. So in hot wall CVD, the nanomaterials or nanofilm formations, that possibility is there in reactor walls. Okay, so but in that is not means that can be avoided or suppressed when it is used cold wall design or cold wall type of CVD if you use. So there is the depositions each possible at the walls, each possibility is there, but that can be avoided when it is used cold wall CVD type. Okay, so this is the basic equipments. Actually, how does it look like? So the CVD equipment. So here you can see there are various components. So here's mass flow controller, gas cylinders, or if it is liquid is there as a precursors, that can be placed here, and then it would be passed through tubes, and there is some that kind of arrangement is there. Then there is a reactor or reactions chamber is there. So through this the starting materials or precursor will pass through this. So here substrate can be placed over there, and then say on vacuum systems is there, vacuum pumps is there. So that vacuum pumps create or maintain the pressures inside of these CVD reactors. So here heating coils is also there for depending upon if we develop plasma or if it is some heating coils also may be placed at this particular locations to maintain isothermal temperatures of the substrate. And then exhaust gas treatment. So if we need to separate out means what are the exhaust gases or byproduct formations is there during the CVD process that may pass through these cold traps. By that way, if there are any toxic gases formations is there, so that can be absorbed over there before disposed to the environment. And then there is a automatic control systems, means the temperature, gas flow, so everything can be, or vacuums, everything can be controlled by using automatic control system. So here say basic CNT formations by using CVD, so it's showing here. So in this case I said this is hot wall furnace. So here substrate is placed over there, and the substrate is heated up with the help of some heating coil or the furnace, and then some hydrocarbons with the inert gas. So depending upon the source materials it is available, that may be CH4 or C2H6 or any other hydrocarbons, that is the source of carbons, ethane, ethylenes, propellants, anything. So we can hydrocarbons, so we can pass through these tubes reactors. So and substrate would be placed here, and we can maintain 850 to 1000 degrees centigrade, or maybe we can use 500 to 700. So depending upon our study of interest, so what type of CNT we are going to prepare, whether it is multi-wall or single wall CNT. So we can pass the reactants, particularly methanes, that is mostly used as a source of carbons for the single wall and multi-wall CNT productions. So here's two different type of growth mechanisms is showing here. That is here one type of growth. Here's catalyst is present over the surface of supports, and here catalyst that is at the top of the CNT. This is CNT basically. When it is grow over the substrates, and then catalyst is moving up detached from the surface of the supports. Okay, so here's the temperature ranges, so that may be 300 to 1200. I said any temperatures depending upon our study we can use or maintains, and then pressures we can maintain at these ranges depending upon their our applications. And growth rate and film quality, that also depends on the gas pressures and substrate temperatures. So these are the things more important. So gas pressures and substrate temperatures for the film formations, growth rates, and film quality formations, for quality of films, whether it is single wall, multi wall, or mixed, depending upon that temperature range as well as pressures of that reactant concentration. The reactants concentrations we can change by changing the pressures or substrate concentrations. Methane gas concentration, that is the reactant, that concentrations we can change. So it has been observed that when means we set the temperatures, we can vary up to this temperature, means 300 to 1200, any temperature ranges we can use for this CVD process. If we use low temperatures or intermediate temperature or high temperatures, so when it is low temperatures, so the reactions would be there over the substrate or the catalyst, and that would be limited by kinetics of surface reactions. And when it is intermediate temperature, that would be maintained during the process, that would be limited by mass transports. Okay, so that we will discuss later. So and when it is high temperatures, means during the CVD process we will use high temperature, the growth rate that would be reduced due to the depositions of precursors. And okay, so from the substrates, so here you can see means reactants, these reactants that is passing, and here is the substrate or catalyst we can say. Then reactants may be when it is passing through the hot chamber, so that reactants may be converted or gas phase reactions might possibilities there. So then some intermediate reactants and byproduct formations is there in the gas phase. Reactant itself decomposed, and this type of things may possibilities there. And then another way, the reactants may be adsorbed over the, these are the reactants that may adsorb over the surface of, this is catalyst or that substrates, that substrate we have taken, so that may adsorb over there. And then these intermediates may come here, and this is initially reactants was there, and then some byproduct is there, they may react over the surface or the substrates, and then some film formations or nanotubes formations would be over there, and then some byproducts or maybe intermediate products that may be coming out with the surface or from the surface of the catalyst or some from the materials where we are going to deposit, so that a layer formations would be there. Okay, so in the step by steps means the reactants may be reactant gases that is that are transported into the reactors, that already have discussed. And then second steps, directly it may diffuse through the boundary layers or maybe adsorbing on the surface. And third step, that is the intermediate reactants and byproduct formations via gas phase reactions and being deposited onto the substrate by diffusion with the step B and adsorption by steps 3. And then surface reactions, surface diffusions by heterogeneous reactions, and in heterogeneous reactions the formation of thin films or coating formations possibility is there. And also I said that in heterogeneous reactions the thin film or coating formations is there, and in also the reactant molecules in the gas phase that would be reacted or decomposed, as a result some byproducts or some unreacted species on maybe some intermediate reactants that may formations is there, that would be dissolved from the surface, and that would be go out or removed from the reactors exhaust or from the reactors outside, that would be going out from the CVD reactors. Next we will discuss about the growth mechanisms. So there are various type of growth mechanisms. So we can means when that substrate or the reactants they come in contact, there is a reactions, and then film formations is there, means CVD growth means carbon nanotubes or nanomaterials, nano layer formations is there. So that reactions will take place, that we can divide it into, or we can say the growth mechanisms by using Langmuir-Hinshelwood type of mechanisms. Here both, if we use multiple reactants, both will adsorb over the surface. This is the surface or catalyst surface of substrate, where both the reactants A and reactants B both will be adsorbed, and then both will react, and then some product formation should be there, that is Langmuir-Hinshelwood type of mechanisms. And other type of is this Airy-Laidlaw type of mechanisms. So in this type of mechanism, so what would happen, so if there are two type of reactants are present, so one would be adsorbed over the surface or the substrate we have taken, and another ones remain in the gas phase, and then reactions will take place. So in this type of also reactions will take place, and then the film formations would be there or film growth, both the way we can see. Okay, next we will discuss about the CNT growth by CVD. So I said there are two different type of growth models have been possibilities there. So if we prepared, suppose some catalyst you have to consider or you have to prepare. So when we prepare that catalyst, so in that catalyst and substrate interactions is weak, or maybe catalyst and substrate interaction is strong. So both possibilities there. So when catalyst and substrate interactions is very weak, or substrate and catalyst interaction is strong. So when it is weak, so then steep growth models will be possibilities there, and when catalyst and substrate interaction is very strong, so then base growth model is there, and then we can get the CNT over the surface. Okay, so here you can see for hydrocarbon that would be decomposed on the surface of the catalyst, formations of the CNT, here alloy that can be used. So then higher catalytic activity compared with the pure metal. So if we use individual metals or maybe alloy type of material, so in alloy it has been observed that higher catalytic activity possibility is there as compared to the pure metals. So pure metals is actives, and combinations of 2-3 metals, formations of that is also actives, but alloy is comparatively more reactive as compared to the pure metals. So in this particular process we can use iron, cobalt, nickel, these are the metals, so we can use for CNT growth or CNT synthesis. And other type of metals, that is copper, gold, palladium, platinum, that also can be used for CNT growths. Okay. So different type of metals depending upon our the study or interest. So any metals that can be used to grow the CNT. Okay. So here top growth models mechanism is showing, and here base growth models I said this is catalyst and this is support and this is the substrate. So over the substrates you can put catalyst and support. So when this catalyst and support interactions is weak interactions. Okay, so here catalyst and substrates they strongly bound, strong interactions is there. So then when that starting materials, let's say substrates will come and interact with the catalyst, then CNT formation, this is basically CNT. So CNT growth would be there, and then catalyst and support interactions is I said weak. As a result, that catalyst will be CNT formations would be there, and catalyst will remain at the top of the CNT. So that is called tip growth basically. And when the same reactants interact with the catalyst, since catalyst and support interactions is very strong, when CNT formations would be there, catalyst remains and attached with the substrate or support, that will not detach from that support. So as a result CNT gradually will forms and growth will be there like this. This is called base growth models. Okay. So these two type of models are commonly used. So depending upon the materials of the catalyst we synthesized, so its calcination temperatures or interactions in between catalyst and support is very important, and based on that two different way the CNT can be growth over the catalyst or the substrates. Okay, so now I will discuss single layer, multi-layer graphenes. So using the CVD setups we can grow CNT at the same time, so graphene also can be developed. So it is single layer or multiple layers of graphenes. So for single layers graphene formations usually copper, that metals would be used. So this is single layers honeycomb type of structures, and here it is multi layers graphite. This is graphites and this is graphene layers, single layers graphene. So it has been started in the year 2004, and then on that times actually has been prepared, produced the graphenes, and then it was isolated and then identifying and characterizing then graphenes. So in graphenes it is actually 2D materials. So 2D materials, sp2 hybridized carbon atoms present. It is hexagonal honeycomb type of lattice present in this. So here in this particular graphene materials said that conductions band and valence bands gap is very narrow. So as a result almost they are touched to each other, forming an exactly zero band gap semiconductors or semi metals, we can say that graphenes. So they have unique band structures, this type of graphene materials. So they can be applied many applications: supercapacitors, composite materials, gas sensor, transparent and flexible electronic device or electrodes to fabricate touchscreen display. So many applications, basically electronic applications, so it can be used. These are the characterizations. So how we can distinguish them? So one layers or multiple layers means graphene and graphite. So here's basic setups or schematic is shown here. So here's we can use, I said, copper materials or copper foils we have to use, or any other metals also we can use as a substrate or as a catalyst to grow the graphenes. Okay, so here the starting materials, so we can use initially what we have to do. So if you want to grow the graphenes over the surface of the copper coil or copper foil, so then initially flow of methanes, that is our starting material source of carbons formations of the graphene. So it would be heated up at high temperatures 1000 degrees centigrade, so we have to maintain, and then hydrogens we can pass for 1 or 2 minutes, and then we can pass removing all hydrogens, and then we can pass the methanes. So once methanes will be passed over the surface of the copper foil, so then the CNT graphene growth might possibility is there, single layer graphene formations is there, and that later we can separate out by dissolving copper or removing copper, that can be applicable or apply for a particular specific applications. There we can transfer that graphenes into that specific application, there we can grow or we can transfer and we can use that later. So and so there are various parameters that would affect the growth of the graphene, so over this system. So there the parameters are the temperatures, gas compositions, gas flow rates, deposition times, heating rate, cooling rate. So these are the components from instrument wise, so or operations wise is very important, that would affect whether it is single layer or multiple layers graphene growth. So I said methane is that starting materials that you have to use to get a single or a few layers of graphenes. So and in this case if we use concentrated methanes, that would get means more than 5 layers, means multiple layer graphene growth formations is there. So if we use low concentrations of methanes, very dilute, so then we can get singles or a few layers graphenes. On when the concentrations would be increased, then multiple layer formations is there. Also the cooling rates that also affect the thickness, means whether it is multiple or single layers of graphenes, different type of defects also, that is depends on the cooling rates. If we cool the systems very fast, so then suppress the precipitated coke or carbons to the single layers graphenes, and if we use moderate coolings during the process, if cooling process is moderate 10 degree centigrade per second, then a thin layers graphene formations are optimized, we can optimize that thin layers. Okay, and this way we can, these are the parameters we can control when CVD process is used and methanes and copper foils is used to grow the graphenes. Next is the applications of the CVD for manufacture of single layers and microelectronics fabrication steps that will show. So here's basically I said copper we have to use as a catalyst or source for that graphene growth. So here's initially graphene copper foils we have taken, and then in our the surface that may be copper oxide present, so then we have to reduce them in presence of hydrogens, and at high temperature you have to use, then that oxides may be converted into, means that is basically it's called annealing process. So copper would be annealed at high temperature in presence of hydrogens. So then in exposures of the methanes and hydrogens, so at high temperatures for 30 minutes, so then some graphenes growth, means that carbons methanes will be decomposed and graphene formations would be there above the surface, and then it is coalescence of the graphenes domains, means enlargements of the graphene plaques and coalescence of the graphenes domains with different lattice orientation that can be observed here. Okay, so initially has started and then over the total surface, so the graphenes will be growth. So that way we can develop the graphenes over the surface of the copper using methane as the source of carbons, and then we have to transfer the graphenes. So once we prepare the graphenes layers, the copper foils, and then we can use that, means in application wise transfer of the graphenes, that is even very important, that is spin coating polymeric layers or roll transfer techniques are there, two techniques are available. So this is initially spin coating polymeric layers. So in this case we have to use initially that graphenes was growth of the copper foils, and after that we have to develop some PMMA or PDMS, that would be thin polymeric layer that would be covered over the surface of the graphenes, means, and then we can surface would be eased out using ferrichloride solutions or with some others acid or nitrate solutions we can use to remove or etching the copper from that surface, and then copper is completely dissolved in this process, and then the floating graphene membranes that would be forms that would be over the PMM is polymethyl methyl acrylates, that is polymers. So over that the graphene membranes would be there. This is graphene membranes over this transparent PMMA, and then that would be transferred to a target substrate. This is our target substrate. So here we can deposit, and then PMMA polymethyl methyl acrylate that would be dissolved by using some solvents. So and then graphenes will be growth over the target substrates, graphene layers will be growth. So this is the spin coating polymeric layer method. So this way you can means graphene should be formed and then that would be transferred, and then another one is the roll transfer technique. So this is another way or technique. So in this way also we can develop some graphene over the copper substrate, and then that would be etched out. Here in this case one polymeric layers or support we need, and graphenes on the copper file is there. Both will pass through these rollers, okay, and then it would be graphenes would be on the polymeric support. This polymeric support initially it was there was nothing. So when it would be passed through this, so graphenes would be transferred from copper file to the polymer supports, and then it would be released the polymeric supports, okay, and then a particular target materials is there, through that or over there so we can deposit that graphenes, okay. So apart from that some 2D materials also we can develop or growth with the help of CVD process. TMDs type of transition metals dichalcogenides, so that is basically molybdenum sulfide, tungsten sulfide, molybdenum selenide, tungsten selenides. These are the heterojunction materials, so that also we can prepare by using the CVD methods. So in the CVD methods, so initially similar like graphenes or CNT synthesis, here also the furnace or reactors or CVD chambers would be heated up, so 650 to 900 degrees centigrade in presence of inert atmospheres, and then we have to place some precursor powders that may be molybdenum oxides that we have to use to prepare MOS2. So in this case we have to pass the sulfur vapors, means initially it was oxide, then that oxide would be converted into sulfates by reactions with the sulfurs at these high temperatures, and that this MOH2 film formation should be there. So in this case the typical reactions what would be the take place during this CVD process or metal sulfide TMD type of materials, transition metal dichalconide formation. So initially metal oxides react with sulfur, these formations is there at low temperatures, and then here's -6 means some amount of oxygens that is losses from the metal oxides, then oxide sulfide formation is there by eliminations of SO2, and then further reactions to forms MOH2 at high temperature. So that way so MO3 converted into MOH2, and then finally MOS molybdenum sulfides, that metals we can this type of materials we can prepare by using this CVD technology. So here is the basics diagram. So as we said that CVD process, so here's heating zones may be multiples also, so heating zone 1, heating zone 2, heating zone 3, that way individual zones also we can control by using some controllers. So at low heating zones sulfur may be placed over there, and high heating zones their metal oxides may be placed over there, and then so when it is passes and then reactions will take place and metal sulfide formations should be there, that would be growth, okay. So thank you. So today is up to this. So we have discussed the CVD process, okay. So thank you.